Alright guys, today we're going to be talking about the disk and washer method. Now we've already talked about the disk method, but the washer method is what happens when you end up with a gap between your actual picture, your bounded region, and the x-axis. So when we try to revolve one of our representative rectangles, right here, around our x-axis, we end up getting this gap. So if we looked at it side on, we would get this, still get this circle. But this would be our outer radius here. So if this was our x-axis, we would have a big radius. But then we've also got this end of our square. Our rectangle is not the entire thing. We end up with a gap in the middle, where a rectangle only really covers the outer portion. So we've got a big radius and a little radius. So our big radius is our distance all the way from the axis to the farthest part of our rectangle. That's our big radius. And our small radius is from the axis to the closer part of our picture, of our whatever our rectangle ends up being. So to find this, we end up having a big circle out here minus a little circle. So let's think back to geometry. If you want to find the area, basically this donut shape, we're just going to take the big radius out here, the big distance, the big circle, minus the little circle. So as far as that goes in geometry, it would be pi big R squared minus pi little r squared. Now generally our bounds are going to be the same, so we're going to really have the integral. You can pull the pi out of both of them, big R squared minus little r squared, and these are not thin. These have some small width. I mean, it's a small width, so the width to make it a volume would be our dx. Now a couple things to note: these squareds you can't pull out from top. It's not here, so you cannot rewrite this as r squared, big R minus little r, quantity squared. Each one has to be squared separately. So this is our formula. And big R, that's going to be the hard part for you guys, is figuring out what big R is. Big R is generally going to be the farthest side minus the axis. Now the axis could be the x-axis, but it doesn't have to be the x-axis. It could be x equals 2, or it could be x equals 4. And since we're squaring it, it doesn't even really have to be above the x-axis. So if we were looking at the second picture, which is what happens to us when we revolve it, if I'm looking for my big R and I want to talk about the bottom half, I would be talking about the farther side, not the higher side. This would be my big R in this case. And then the inside edge would be my little r. So it's not top minus bottom, it's farthest to closest, really. So you've got to figure out what the farthest part of your rectangle is minus the axis, and then your little r is going to be your closest minus the axis. Alright, let's see how that looks in an actual problem. Alright, so we've got a couple of problems here. They're all using the same graph, but they're all revolving about different things. So 2x squared is a parabola. Instead of going up 1, it goes up 2. Instead of going up 4, it goes up 8. 2, 4, 6. Alright, so that goes off the screen really fast. But we generally have, oh wow, that's not so good. Let's try that again. So we generally have a pretty steep parabola. And it's bounded by x equals 2. Let's do that in green. And y equals 0. So I'm hoping we're all thinking the exact same area here. Right down here. Now, if I'm revolving this about the x-axis, there's no gap between the bottom of it and the axis. So in this case, I don't have to worry about the shell method. Or not the shell method, but the disc and washer method. It's just really disc. Our big radius is the distance from the top of our rectangle to our axis. So this is our big R, which is just our 2x squared minus our axis of 0. Our little r is the bottom minus the axis. So it's really just 0 minus 0, or 0. So we have pi. Our bounds are going to be, this is 0, and this is 2. So 0 to 2. We want our bounds in terms of x. And then we just have our big R squared. So 2x squared squared minus our little r, 0 dx. That's our formula, and if you want to do this by hand, you get pi integral of 4x to the 6th from 0 to 2, which you can figure out either in the calculator or by hand, but you want to make sure that you square the 2 as well. Alright, now this is not so bad. What gets a little bit trickier is when you start revolving about different axes. So line y equals 8. So I'm going to make these actually go by 2. So this would be 2, 4, 6, 8. So I want to revolve it about this line right here, which is not going to change our picture much. I'm still going by 1 on the x's, so this is going to make it a little bit more of a squat graph. So I'm not changing really my x's, but I'm just changing my scale on y's. So this is 2, 3, 4. So my picture is still the same. I'm still looking at this rectangle here, except now we're revolving it about this axis up here. So the distance from the far side of the rectangle to the axis is my big R. The distance from the close side of my rectangle to the axis is my little r. So to find the big R and find the little r, you're really just taking this distance here. Now this distance you can either think of top minus bottom or your function minus your axis. And the reason why it doesn't matter is because you're going to be taking r squared here in a second. So even if you have it upside down, it doesn't matter too much. I think I said that I wanted to go the farthest minus the axis, but I think it probably makes more sense to have the signs being positive. So it's still the farthest to the axis, but we want to take, in this case, to make the r make more sense, big R would be our axis, which is 8, minus the far side here, the far function, which is 0. So this distance is just 8. The little r is the part that's changing. It's going along the parabola.